Section. Introduction. For many years, scientists have been curious about whether it's possible to optimize neural networks without using backpropagation to differentiate the loss function. One intriguing idea, first proposed by some researchers, is to select a random direction, calculate the derivative of the objective in that direction, and then take a step in that direction, scaled by the derivative. This approach, which uses the model's weights, is a clever way to estimate the true gradient without bias. This method has gained renewed interest recently because directional derivatives can be computed very efficiently using forward-mode differentiation, which doesn't require the large memory capacity that backpropagation does. However, as the complexity of the optimization problem increases, so does the variance in the estimator, which can slow down convergence. If the network has n parameters, the similarity between the estimated and true gradient decreases to 1 over the square root of n for neural networks with billions of parameters. This estimate is almost perpendicular to the true gradient, making it impractical. At first glance, it might seem that random guessing is the best we can do without additional loss functions or access to labels. However, the intrinsic dimension of gradients is often much lower than n, suggesting that we might be able to improve on this. In this paper, we find that the structure and activations of the neural network significantly constrain the gradient even before a loss is computed. In other words, we have information about the gradient before we even see the label. This leads us to ask, how can we use what we know about the network architecture and incoming features to make better gradient estimates? By carefully examining the structure of neural network gradients, we show that it's possible to produce estimates with much higher similarity to the true gradient, even for networks with millions of parameters. We then compare these estimated gradients to the true gradients from backpropagation to understand their effects on neural network optimization for MLPs and local mixer architecture. Next, we analyze the variance and optimization properties of these estimates to highlight their improved convergence and study limitations such as bias. Finally, we demonstrate an unexpected, self-sharpening phenomenon, where the training dynamics induced by these estimates make it easier to guess the gradient over time. This phenomenon leads to more than 95% training accuracy on CIFAR10 without backpropagation. However, these advances come with some important limitations, which we also discuss. While the methods outlined in our work provide theoretical advances in our understanding of gradient structure, they are not yet ready for practical use. For example, they are still significantly slower than backpropagation with gradient checkpointing. Currently, all approaches in this space fall short of backpropagation level performance on larger problems. Gradient-based learning is the dominant paradigm for neural network training, and backpropagation has long been the dominant method to calculate neural network gradients. Its dynamic programming formulation allows it to compute the gradients remarkably efficiently. In contrast, alternatives such as real-time recurrent learning, RTRL, have not enjoyed the same popularity due to significant computational overheads. However, as our models and data continue to get bigger, backprop presents some crucial limitations to scaling. For instance, backprop requires keeping track of intermediate activations, thus requiring a large amount of memory. For example, a GPU that can run inference for a 30 billion parameter LLM can only train a 2.7 billion parameter LLM. Additionally, backprop requires synchronization between the forward and backward passes, called backward lock, and this limits the efficiency of highly parallelized hardware. These issues warrant revisiting backprop alternatives that scale better. This is further exacerbated by the emergence of new learning paradigms like fine-tuning, transfer learning, and test-time training, which changes training from a one-time process to something persistent and online. Randomized automatic differentiation, RAD, tackles the memory bottleneck by sampling random subgraphs of the overall computation graph and only computing gradients over those. Mezzo uses zero-order optimization for fine-tuning pre-trained models. Its experimental results, along with theoretical arguments showing that convergence depends on the rank of the Hessian rather than ambient dimensionality, demonstrate the utility of backprop alternatives for large models. Some researchers leverage sparsity to improve the performance of RTRL in the space of recurrent networks. Others compute the gradient for energy-based models using the same type of computation as in the forward pass. Some propose an alternative based on the directional derivatives, computed using Jacobian vector products, JVP, with the distinction of having comparable computation costs to backpropagation at the algorithm level. However, on many practical tasks, such methods are far behind backpropagation. For an n-dimensional problem, some researchers show that this method incurs an n times slowdown over ordinary gradient descent. Others provide further theoretical and empirical evidence that the curse of dimensionality prevents this method from scaling. Similarly, some researchers can train a small MLP on MNIST but not a ResNet on the CIFAR10 dataset. This weakness stems from the suboptimal proposal directions used in these directional derivative methods. Work from some researchers also demonstrates this slowdown and addresses it by including local loss functions after each block in the network. Some researchers use local losses with auxiliary neural networks to generate a gradient guess. They show excellent results on relevant models such as ResNet 18. While our work is not directly comparable since we don't use any losses to generate guesses, these approaches may be combined in future work. Section Summary. Researchers have explored the possibility of optimizing neural networks without using backpropagation, and one approach is to make intelligent guesses about the gradient based on the network's architecture and input features. By analyzing the structure of neural network gradients, it is possible to produce guesses with higher similarity to the true gradient, leading to improved convergence. However, these methods are not yet as efficient as backpropagation and have limitations in practical use. Section. Methods. In this section, we'll explain the methods we've developed to reduce the guesswork involved in our process. We'll start by discussing constraints based on architecture, then move on to constraints that rely on our understanding of the relationship between gradients and activations. We'll be sharing our code when we publish our findings to encourage further research. Let's start with some background and notation. We're trying to optimize a multi-layer perceptron, MLP, that has k layers and n neurons in each layer, using ReLU activation functions. The weights of each layer are represented by W_1, W_2, W_k. At any given layer I, we take the incoming activations, represented by X_I, multiply them by the weight matrix W_I to get the pre-activations, S_I, and then apply the ReLU function to get the post-activations, X_I plus 1. We then pass X_I plus 1 to the next layer, and eventually calculate a loss, L. Our goal is to compute or approximate the gradient partial, L, partial W_I to train that layer. We do this by guessing a direction, epsilon, and computing the loss directional derivative, epsilon, CDOT nabla, L. In modern automotive frameworks, this can be computed efficiently using a forward mode differentiation operation called Jacobian vector product, JVP. We use the terms directional derivative and JVP interchangeably. Given the guess direction, epsilon, and its JVP, epsilon, CDOT nabla, L, the product hat, G, equals, epsilon, CDOT nabla, L, epsilon, is an unbiased estimator of the gradient. For large models with n parameters, this estimate hat, G, resulting from uniform random guess directions epsilon will typically have low cosine similarity to the true gradient nabla, L, i.e., frac, ver that, G. Nabla, L, vert, ver that, G. Vert nabla, L, vert, equals O, frac, 1, sqrt, n. This quantity is captured by the variance of the estimator. We aim to create guesses that lower the estimator's variance at the cost of introducing bias. The current best method is to guess the unknown partial L, partial W_I uniformly at random via spherically symmetric Gaussian. But we think we can do better. By unfolding the computation, we can identify exploitable information to refine our gradient guesses. Considering the computation at layer I, where S_I equals W_I X_I represents the pre-activations, applying the chain rule reveals a crucial insight. Partial L, partial W_I is essentially the outer product of the unknown gradient at future layers partial L, partial S_I and the known incoming activations X_I. Notice in particular that partial L, partial S_I is of significantly lower dimension than partial L, partial W_I. This leads us to our first insight. We can guess the low-dimensional partial L, partial S_I and use the known X_I caret top to compute a much lower variance guess for the high-dimensional partial L, partial W_I. We have reduced the guessing space from O, n squared, to O, n. Practically, for neural networks with millions of parameters, this means guessing in a few thousand dimensions. This guess consists of perturbations of pre-activations, S_I, similar to the work of, and we denote this as activation perturbation. Let's keep unfolding. The next step is to take the ReLU of S_I to obtain X_I plus 1. Our second insight is that by the very nature of ReLU activations, the Jacobian matrix partial ReLU, S_I, partial S_I will be a sparse diagonal matrix. It is diagonal since each input controls one and only one output. Furthermore, this matrix will also typically zero out some entries of the incoming gradient. This suggests that we should guess only the surviving entries of partial X_I plus 1, as determined by that sparse and diagonal matrix known at guess time. Although the exact fraction depends on many factors, including the data and optimizer, the sparsity ratio is typically 0.5 at initialization. This further decreases the dimensionality of our guessing space and, consequently, the variance of our guesses. Let's unfold one last time, looking into the next weight matrix W_I plus 1. Again, we apply the chain rule, now at S_I plus 1. As before, the future gradient partial S_I plus 1 is unknown and must be guessed. But we know that it will immediately be multiplied by W_I plus 1, top. While this does not necessarily give a hard constraint on our guess, our third insight is that W_I plus 1, top often effectively has low rank. We can constrain our guesses to lie in the image of W_I plus 1, top by multiplying our guess with it to lower the dimensionality of our guessing space further. To summarize, we know that at guess time, all of these quantities are known except for partial S_I plus 1, which we guess as random normal with zero mean and unit variance. We then apply a series of constraints to mold it into a much more effective guess for partial W_I. We refer to the combination of these methods as W_top. We can also incorporate the local architecture information into the gradient guess by using a method we call partial backpropagation. This involves using a random normal guess for the neurons X_I plus L, which are L layers downstream of the current layer, and backpropagating through the intermediate portion of the graph. This approach requires storing the intermediate activations for the L layers, and in the full limit, is equivalent to regular backpropagation but with a random error vector. In our experiments, we find that L greater than 1 has diminishing returns, so we stick to L equals 1. All the methods we've discussed are special cases of this general approach. Section summary. In this section, the authors propose methods for narrowing the guess space and optimizing a multi-layer perceptron, MLP, with ReLU activation functions. They introduce architecture-based constraints and constraints based on the relationship between gradients and activations to improve the accuracy of gradient guesses. By leveraging the computation at each layer and exploiting the sparsity and low-rank properties of certain matrices, they reduce the dimensionality of the guessing space, resulting in lower variance and more effective gradient guesses. Section. Feature-aware gradient guessing. We're going to delve into a concept we call feature-aware gradient guessing. This involves unrolling the steps of stochastic gradient descent, SGD, and observing that the activations and gradients of a neural network tend to lie in the same subspace. We've illustrated this in a figure. Our aim is to create random vectors that occupy the same subspace as the true gradient, which is the rate of change of the loss function with respect to the activations at the next layer. We do this by using a random mix of these activations as our guess. Here's a simple way to think about it. Imagine we have a downstream weight matrix that's being updated over time using SGD with a certain learning rate. At any given time step, we can expand the term representing the rate of change of the loss function with respect to the activations. If we ignore the initial weight, we find that the desired gradient roughly lies in the subspace of previously generated activations. While this explanation makes a few assumptions, such as the use of an SGD optimizer and small initial weights, our experiments show that the subspace of activations often aligns well with the gradient subspace. We use this observation to generate a guess for the rate of change of the loss function with respect to the activations by taking the current activations and calculating random linear combinations of all the training example activations in the batch. We call this method activation mixing. In summary, we propose 4 variants. 1. Activation perturbation, which creates guesses in the activation space rather than the weight space. 2. Activation mixing, which uses mixtures of activations as the guess. 3. Transposed weight matrix, which multiplies a guess by the transposed weight matrix to produce a guess. And 4. One layer downstream, which backpropagates a guess from the layer next to the current layer. We then evaluate these methods, comparing their cosine similarity, optimization performance for one step, and then optimization performance for multi-layer perceptron, MLP, and local mixer architecture. We also analyze phenomena like bias and report an unexpected phenomenon we call self-sharpening. To compare each method's gradient guess, we use an MLP with a depth of 6 and a width of 1024, trained on the CIFAR10 dataset. We measure the cosine similarities of guessed gradients for each method and plot the results. We find that, on average, our proposed methods produce cosine similarities that are hundreds of times higher than directional descent. We also directly compare each method's effectiveness in terms of loss reduction from one step, relative to backpropagation, and further search over multiple step sizes for each method to make the comparison as fair as possible. We find that our methods are thousands of times more effective compared to directional descent in the one-step regime. We then conduct experiments to train MLPs using our proposed methods on 4 commonly used datasets: MNIST, SVHN, CIFAR10, and CIFAR100. The MLPs were configured with 4 different depth and width configurations. We find that while our proposed methods outperform directional descent, there is a large gap between these methods and backpropagation, and the gap grows larger with more complex datasets. We also test our method's effectiveness for large-scale models, evaluating our model on the local mixer architecture. We find that our method generalizes better than backpropagation on the local mixer architecture. We also measure the behavior of our methods in the limit of a large number of guesses. For an unbiased method such as directional descent or activation perturbation, more guesses result in a better cosine similarity. This is not the case for biased methods, as decreased variance is traded off with increased bias. To better understand the effect of bias and low-high cosine similarity on the network training accuracy, we construct a version of directional descent where we artificially modify its guess to have similar cosine similarity to the transposed weight matrix method. We find that while the transposed weight matrix method converges significantly faster than the original directional descent, its bias hampers its convergence speed. In another experiment, we explore the interaction between bias and optimization dynamics, specifically momentum. We find that in the presence of momentum, these two diverge from each other. However, the two training curves no longer diverge when momentum is removed. Finally, we compute the cosine similarity between the true gradient and its projection onto the subspace spanned by activations. We find that the activation subspace consistently requires much fewer basis vectors for a significantly better approximation than a random subspace. Section summary. The authors propose a method called feature-aware gradient guessing to generate random vectors in the same subspace as the true gradient. They use a random mixture of activations as the guess and show that the activation subspace is often well aligned with the gradient subspace across depths, widths, and training epochs. Their experiments demonstrate that their proposed methods are more effective and produce higher cosine similarities compared to directional descent in terms of gradient guess and loss reduction. Section: The self-sharpening phenomenon. We've observed an interesting, self-sharpening behavior in some methods, where the range of possible guesses becomes more focused or sharpens during the training process. This results in a better match to the exact gradient, as shown by an increase in cosine similarity. This is in contrast to other methods, like directional descent, where the cosine similarity remains almost the same. We're not entirely sure why this happens, but we think it might be due to a feedback loop that reduces the rank of downstream weights. This reduction in rank narrows the range of guesses, which in turn makes the updates less varied and further reduces the rank. To take advantage of this, we've developed a gradient guessing scheme that uses random uniform noise in the one-layer downstream gradient guess. To speed up convergence, we replace the last layer's guess with the true error vector, which is local information and doesn't require any backpropagation. This change significantly increases the cosine similarity to values as high as 0.6 over time. As a result, the training accuracy also reaches over 95% on CIFAR-10. However, while this approach achieves high training accuracy, it also hurts generalization, reaching only 33% test accuracy. We think that the biased guesses, which are dominated by a few singular values, lead to lower rank weight matrices, which in turn lead to higher cosine similarity over the course of training. We've modified the guessing method by computing the singular value decomposition of W and raising its singular values to various powers. Higher powers lead to a more imbalanced distribution, with a few singular values dominating the rest, whereas smaller powers lead to all singular values becoming nearly equal. We've found that when a few singular values dominate, it leads to a lower weight matrix rank and higher cosine similarity, which increases over the duration of training in lockstep with the lowering rank. Conversely, the lowest powers lead to the smallest increase. We've also looked at the source of the bias present in our proposed methods. We started with the unbiased estimator, which uses the Jacobian vector product, JVP, and we computed the expectation of this estimator. We found that in expectation, the gradient guess is equal to the original guess scaled by the covariance matrix of the guess. Thus, the bias is the difference between the covariance matrix and the identity matrix in the subspace that the gradients lie in. For our proposed estimators, this is easily shown to be false. Activation mixing uses random mixtures of activations as the gradient guesses, and thus its covariance matrix is the same as the covariance matrix of the activations, and thus non-identity. Our methods rely on these covariance matrices being low rank and well aligned with the gradient subspace to produce high cosine similarity guesses. However, as a result, our expected guess is also scaled by these covariance matrices, thus biased. In future work, we hope to use this information to undo the bias caused by these non-identity covariance matrices. We've also found that using more layers in partial backpropagation isn't always better. In practice, the bias can increase with each additional layer. We've shown this with a simple toy example. We've also found that our methods can significantly reduce the guessing space by using the knowledge that the true gradient lies in the range space of the accumulated Jacobian for layers. However, the bias of the estimate can increase with more layers, as shown by a simple case where each Jacobian is twice the identity matrix. Section Summary. The self-sharpening phenomenon refers to the narrowing of the guess space during training, resulting in improved cosine similarity to the exact gradient. This effect is hypothesized to be caused by a feedback loop of decreasing rank of downstream weights. However, while self-sharpening achieves high training accuracy, it negatively impacts generalization. Additionally, the bias present in the proposed methods is attributed to non-identity covariance matrices, and future work aims to address this bias. The use of more layers in partial backpropagation can increase bias, as demonstrated in a toy example where the bias increases with the number of layers. Section. Summary and discussion. In our discussion and summary, we've demonstrated that it's feasible to generate gradient estimates with significantly higher cosine similarities than those produced by directional descent. We've also examined the optimization characteristics of these estimates, emphasizing their enhanced convergence and certain limitations, such as bias. We've found that bias is a significant obstacle to the scalability of our techniques. However, we've also observed a self-sharpening phenomenon that enables us to achieve over 95% training accuracy on the CIFAR-10 dataset without the need for backpropagation. Despite this, the model doesn't generalize well. These discoveries not only hint at the potential benefits of harnessing the structure in gradients, but they also reveal new phenomena that could pave the way for future research. Since bias is a significant hurdle, overcoming this issue could lead to substantial advancements in applying these techniques to large-scale problems. This could be particularly beneficial for training models with model parallelism, and a deeper understanding of gradients could aid in the development of more efficient optimization pipelines. Effective gradient estimation methods could also decrease memory usage and enable larger models to be accommodated on consumer-grade hardware. This could democratize access to training, fine-tuning, and personalizing deep learning models. Another intriguing area for future research is the application of these methods in biologically plausible learning algorithms. The problem of scalable credit assignment within biological constraints remains unsolved, and many proposed solutions involve some form of random perturbations. Our suggested methods could be integrated with these approaches, as well as with recent data-based gradient estimation schemes. Heuristics such as aligning activation and gradient subspaces could be applied to associative memories in general. This could be beneficial for narrowing down the guess space in such settings.